Okay, now following the same scheme that we used in the earlier sections where we've constructed the three-phase generator, and now we're going to connect resistive loads to the output of each of the three phases. Now, when you're thinking about this, we're talking in terms of three different loads connected to the three different phases. When this is actually done, in real applications, it's really a singular load, even though we're representing it as three separate loads. So these three phases would be connected to, say, a motor, right? And but for our understanding of the operation, we're looking at these as three separate phases, and it makes it easier for us to understand. All right, so let's take the three-phase generator, connect loads so that we can get current flowing, and then look at the power output. Okay, so really dial in on this section. Make sure that you understand what's going on with this. It may be one of the few times you actually get into this kind of detail with why three-phase works the way that it does. And so stay with me here as we walk through this. Okay, so here is coil 1, which we're calling, what we're calling that, A1. And so what we did is we connected wires from this coil to this resistive load here. And so now current flows through that load. All right, so when we did this, it took 2 wires to make those physical connections from the coil out to the load. Okay, now we're going to repeat that with phase B, right? And here is the phase B coil right here, right? And then from there, we connected to the resistive load, and we ended up with that segment of this. Okay, and together with that is this, we've got 2 more wires, we'll call this wire 3, and this is wire 4. And then the last phase here, let's go with a different color. Here is the 3rd coil, and along with that is the wire connections to the load. And again, we've got a 5th and 6th wire. Okay, so when you look at this total configuration and what happens here, this thing gets so sort of dense that we have to sort of pull these things out of here. You really couldn't show the rotating magnet with the coils and get all this down into a thing that was easily understood. But this is just 3 coils now instead of 2, and we would call this a 6-wire 3-phase system. Okay, and that is one type of system that you might encounter. And the loads here, like I told you before, those are all sort of consolidated in actuality in terms of maybe a motor or some other type of 3-phase load. Okay, now together with that, since these are all resistive loads, the voltage and the currents are all in phase with each other, and they all represent this 120 degrees of phase difference throughout there. And that is seen with this representation here. And let's see, what else could we talk about here? And all that means is each one of these are the same. Each one of the phases are the same. All it means is they reach their peak voltage 120 degrees apart. That's all that represents there. So what we can do with each one of these, and I wish, that we had a representation that would show the three phases of electricity like we had with two phases. So let me try something here. Hold on. Okay, I can't write on this like I would want to, but so when I'm at phase A, there would also be a current that would be associated with, um, phase A. It would be less than, the voltage, right? But it would be, it would run in the same um, way, right? Uh, across, just a lower value, but it would be in phase because it's a resistive load. Okay. And so what we could do with each one of these phases is we could plot the um, instantaneous voltage times the instantaneous current and plot the power curve. Okay, so that's what I was trying to get to. Unfortunately, and I don't really know why this is, it shouldn't be this way. We should have a continuation of what we had with phase one and phase two, where we had these graphs of the power curve. So I'm going to try to create one and see if to help make my point here. Okay, after this attempt, I won't quit my day job as a textbook illustrator. But what I've tried to do here is, this is from the two-phase generator, and we had the instantaneous power output, right? And we had two phases of that. So this was one, this was two. And so what I'm trying to show is there would be a third phase. The sequence of this, instead of being 90 degrees, would be 120 degrees, between the peaks. Like if this is 0, then this would be 120, and this would be 240, right? So there's 120 degrees difference. So this would be phase C output. Now, without going into the derivation of, working through the math of this, where the total power output from the two-phase generator was here, right? Which was the actual steady state, or that's not a good term to use. That means something else actually. But the power output is constant, and it was twice what the single phase was. Okay, because in the single phase power, the power output that we looked at here was 1/2 the peak. So when we go to the two-phase power output, we see that it is constant and is equal to the peak, not half the peak. But if we look now at three phases of power, the power output is 1.5, 1.5 times more than the peak of the two phase. Okay, so it's not a doubling again, but as he says, if we add all the instantaneous powers of all three resistors, we discover that the resulting power is constant, as in the case of the two-phase generator. First off, you don't have the pulsing, you have a constant power, which is good. And then he says the total output of the three-phase generator has a magnitude of 1.5 the peak. Okay, so we went from half of the peak power to the peak power to 1.5 of the peak power across there. And then because this is constant, the mechanical power, needed to drive the rotor is constant. So the three-phase generator, there's no vibration there. It's not that pulsing effect that you get. And the power flow over the transmission line is also constant across there. Again, I wish I could merge all these, graphs and show this, but I don't have that available. And I've searched so many different places to try to find that, but just trying to make that point for you. Now, let me stop and we'll work example 2. We'll make this part 1 of 8.7 for power output, and then there'll be an 8.7 part 2 where we work through example 8.2.